Hello, my name is Shahnawaz. We begin this lecture with the following corollary to the previous theorem. So, if an abelian group G is an internal direction of, suppose this G is internal direction of S and T, then the Cartesian product of S and T is isomorphic to their internal direction via the map an element here, that is some little s and little t, it goes to their sum, and conversely every external direction is an internal direction. Every external direct sum is an internal direction. And that is given abelian groups S and T, abelian groups S and T, then Cartesian product of S and T is equal to direct sum of S prime T prime, where this this S prime contains the elements of the form S, 0, where S is in S. And this is subset of S cross T, and T prime contains all those elements of S cross T whose first component is 0. Now this is what we have to prove. So first we are going to prove that Cartesian product of S and T is isomorphic to their internal direction. So for that, let us define a map. Let f from S cross T to their internal direction be a map defined as f of st, it goes to s plus t. Now note that this map is well defined because an element s comma t, it won't, suppose if we have an element here s and t, it cannot be mapped to two elements, say s plus t and s prime plus t prime. this won't happen because every element here has a unique expression of this form. So these two elements must be equal. So this map is well defined. So let f from s cross t to s direction t be a map defined as this, which is clearly well defined because of uniqueness hypothesis. Now to prove f is a homomorphism, we have f of little s t plus little s prime t prime. Now this is same as f of s plus s prime t plus t prime. Now by definition of this f, this is equal to s plus s prime plus t prime, and this is same as s plus t plus s prime plus t prime, because g is given to be abelian, so we can write s prime plus t prime as plus t as t plus s prime. So now this element over here, this is same as f of st plus this element over here, this is same as f of s prime plus t prime. So this implies f is homomorphism. Therefore f is a homomorphism. Now to prove that f is bijective, i.e. to prove f is 1 and onto, there are two ways to prove f is bijective. One way is to show that f exhibits its inverse, i.e. there exists some g from now let us do this as follows. To prove f is bijective, it suffices to prove, note that a function is bijective if and only if it is invertible. So to prove f is bijective here, it is enough to show that f is invertible. That means we had to prove there is some other function g such that f composite with g and g composite with f are both identity functions, and supposed to prove that f is invertible. Let us define g from direct sum of s plus t to st as this s plus t goes to s comma t. Sorry, it is s cross t here, so it is s comma t here. Note that again this function is well defined because of uniqueness hypothesis. Now f of g, now g is a function from s plus G is function from direct sum of S plus T to S cross T, and F is a function from S cross T to direct sum of S and T. So this is G here, this is F here. Now this composition, this is a map, this is a map FOG. So this FOG is a map from S plus T to S plus T. Now we have to prove this is identity map on S plus T. So now such that f of G of S plus T, this is f of G of S plus T, this is same as f of S comma T by definition of G, and this is same as S plus T by definition of F. So S plus T goes to S plus T, so this implies f of G behaves as an identity function of on, this behaves as an identity function on S plus T. Similarly, we can show that GOF. Note that f is a function from S cross T to S direct sum T. So this is what f, and G is a function from direct sum of S and T to their Cartesian product. This is function G. So this composition is GOF. This is function from also GOF is a function from Cartesian product of ST to Cartesian product of S and T, such that G of F on ST is same as G of F of ST. This is G of, now F sends this two tuple ST to S plus T, and by definition of F, this sends this element over here to S comma T. So GOF sends ST to ST. So this implies GOF behaves as an identity function on S cross T. Hence F is invertible. Note that this F is the function from S cross T to S direct sum T, which turns out to be the homomorphism as well as bijective. This implies that S cross T is isomorphic to, hence S cross T is isomorphic to their internal direct sum. Now to prove second, note that we have S prime to be a subgroup of the form to be a subgroup of S cross T, which contains all two tuples whose second component is 0. So this is subset of S cross T, not just a subset but a subgroup. Now this, note that S prime is isomorphic to S, is isomorphic S via the map S comma 0 goes to S. What does that mean? We have S prime over here. We claim that this S prime and this S, they are isomorphic via the map. Now this contains elements of the form S comma 0, two tuples whose second component is 0, and if we define a map from S prime to S, which sends an element of this form to S, we claim that this map, say suppose this map phi, we claim that this map P is isomorphism. It is very easy to prove phi is isomorphism, so it is left as an home assignment. Note that this S prime is isomorphic to map is why the map is, and T prime, which contain all two tuples of S cross T whose first component is 0. So this is again a subgroup of S cross T. This is isomorphic to T via the map via a map which maps an element 0T to T. So via this map, this is again an isomorphism. Now S prime plus T prime, this is same as S cross T, since if I take any element over here, S and T here, this S and T is same as S comma 0 plus 0 comma S, 0 comma T. Now this element over here, this belongs to S prime plus T prime. So these two sets are equal. Also S prime intersection T prime. Now S prime contains all elements whose second component is 0, and T prime contains all the elements whose first component is 0. So their intersection contains only this element 0 and 0. So this implies that each element of S prime plus T prime can be uniquely expressed as an element like this and this, with the condition that their intersection is singleton. This implies that this is direct sum over here. This implies S cross T is same as S prime direct sum T prime, because their intersection is singleton. So this is the proof. Next we are going to prove a lemma which states that so we have the lemma: if S1, S2 through Sn are subgroups of an abelian group, say G, then then G is, let us state this lemma like this. Let G be given as S1 plus S2 plus so on plus Sn. G is given to be an abelian group, be an abelian group, where S1 through Sn are abelian subgroups, of G. Then an element G in G can be uniquely expressed as G is equal to little s1 plus little s2 plus so on plus little sn, if and only if this intersection Si intersection with S1 plus so on plus Si cap plus so on plus Sn, this is singleton. This cap here, this represents that this term is omitted from the sum. This is omitted from the sum, that is, and this sum contains here S1 plus so on plus Si minus 1 plus Si plus 1 plus so on plus Sn. So this expression over here, this is same as this expression. One can see that in this sum the term Si is omitted. So we have denoted this expression like this, where this cap means the term Si is omitted. where where cap represents that, where say where Si cap represents that the term Si is omitted from the sum, is omitted from this sum. Now proof. So let us first assume that each element G in G is uniquely expressed as, let G belongs to G be uniquely expressed as G is equal to S1 plus so on plus Sn, where Si belongs to Si for all 1 less or equal to I less or equal to n. Si belongs to capital Si for all I. So we assume this assumption, we assume this thing over here, that each element G in G is uniquely expressed as an element in S1 plus an element in S2 through an element in Sn. Now what we have to prove, that we have to prove that this intersection over here, this is singleton. So we'll assume that some element X belongs to in this intersection, and we prove that that element is nothing but 0. Let X belongs to Si intersection S1 plus so on plus Si cap plus so on plus Sn. That means note that here this Si is omitted. This is a sum S1 through Si minus 1 plus Si plus 1 to Sn. So this implies X belongs to Si and X belongs to S1 plus so on plus Si cap plus Sn plus so on. Or X is equal to some little Si, because X is in Si. It may be of a form some little Si, where Si is in Si, and this X, note that this X is in this sum. Now each element in this sum has the expression of the form S1 plus so on plus Si minus 1 plus Si plus 1 plus so on plus Sn. Now this X is same as Si and this X is same as this sum. This implies, or Si is same as S1 plus so on plus Si minus 1 plus Si plus 1 plus so on plus Sn, or 0 is equal to minus Si plus S1 plus so on plus Si minus 1 plus Si plus 1 plus so on plus Sn. Now 0 has 0 can be expressed like this expression, but note that 0 has also an expression, but 0 can also be expressed as, can also be expressed as 0 is equal to 0 plus 0 plus so on plus 0. Now note that we have assumed that each element G in G can be uniquely expressed as this sum over here, as the sum of elements of Si's. Now in particular 0 is also in G, so 0 can also be expressed uniquely as a sum of elements of Si's. Here we have proved that 0 can be expressed in two ways. This forces these two expressions to the fact that these Si's are all 0. By uniqueness hypothesis, so let us keep this as equation first and second by uniqueness hypothesis. We obtain from first and second that Si is 0 and Sj is 0 for all j. That is x is 0. So this implies this x is 0. This means that this intersection is singleton and contains only one element, i.e. Si intersection with all other i's other than Si. That is S1 plus so on plus Si cap plus Si cap plus so on plus S, and this is singleton. Now we'll assume that this thing holds and prove that each element in G can be uniquely expressed as sum of elements of Si's. Conversely, assume that Si intersection with remaining Si's, sum of remaining Si's. Assume that this is singleton. Now we have to prove that each element in G can be uniquely expressed as sum of element of capital Si's. Let G belongs to G has two expressions. Say G is equal to S1 plus so on plus Sn, and G is equal to S1 prime plus so on plus Sn prime, or S1 plus so on plus Si plus Sn. Now G is this and G is this. This implies this sum over here is same as the sum over here, S1 prime plus so on plus Sn prime. Or now in this sum over here there is somewhere Si, so let us keep Si over here and take an Si prime over here to this side. Now the remaining Si's, we will shift them to the right hand side. So we have Si prime plus so on plus Si prime cap. And this cap means this term is not there because we have shifted this term over here. Si prime is here, plus so on plus Sn prime minus. Now we have shifted these S1 through Sn to the right hand side except this Si. So we are shifting right hand side these Si's. S1 plus so on plus Si cap plus so on plus Sn. Now these two expressions, they are equal. Now this element, this belongs to Si, and this expression over here, this is in, now these Si's are in capital Si, so this Si is in Si, this Si prime is in Si, so the difference is in Si. Similarly, this sum over here, this belongs to S1 plus so on plus S1 si cap plus so on plus sn. This sum over here, this belongs to this thing, and this sum, this belongs to this thing, so their difference is also here in this sum. This means that now being since they are equal, this means that this is in si, but this sum is equal to this sum over here, this difference over here, and this difference lies in this sum. This means this si minus si prime is also here. So this implies this belongs to the intersection. This implies si minus si prime belongs to si intersection s1 plus so on plus s1 si cap plus so on plus sn, but this intersection is given to be equal to the singleton set. So this implies si minus si prime is equal to 0, or si is equal to si prime. Now since this is true for any arbitrary si, this is true for all si's. So this means that these two expressions over here, s1 is s1 prime, sn is sn prime, so G has the unique expression of this form. So this completes the proof.